Hello.
Hello.
Yeah. Am I audible?
Yes, sir. Yes. Good morning, sir. Yes, audible, sir.
Okay. So I just checking the video. Okay. So my video is clear.
Yes, yes, sir.
Okay.
ठीक है अभी दोनों को बंद कर दो हाँ नहीं तो हाँ
Sir, good morning, sir. You are not audible.
Yeah, sorry. I am now. I have put on my mic. Am I audible now?
Yes, sir. Yes, sir. Good morning, one and all. Good morning, sir. And welcome to the last day of online AICT Atal FDP program on quantum computation and information science, organized by Geetam, deemed to be University Bangalore campus. First of all, before starting of the session, I would like to take this opportunity to introduce our resource person, Professor Dr. Prasant Kumar Panigrahi. Presently, Sir is working as a professor in the Department of Physical Sciences, Indian Institute of Science, Education and Research, Kolkata. He has done his PhD from the University of Rochester, Newark, USA. He has done his postdoctoral fellowship in Canada, in Chicago. His main research interest includes quantum computation and quantum information, nonlinear dynamics, field theory, and Webler transform. It's really our honor, sir, to have you as a resource person. We are welcoming you, sir.
Thank you, Sunita. So we can start now.
Yes, sir. Yes, sir.
Okay. So I will. इसको क्या छोटा कर सकते हैं पूरा फुल स्क्रीन में It's okay. Okay, so thank you, Sunita, for first of all inviting me to give this talk here. And so I'll be talking about quantum computation and technology. And in between, if you have some query, you can always ask through the chat box, or you can intervene me and also open your microphone and ask, because it's a long session. So you should be comfortable, and any time when you have question, it can be of the discussion type. So I don't mind, you can stop me. So quantum computation and technology. So you may ask, quantum mechanics is fairly old subject. It has been in existence since 1925-26. And why now? And particularly, why technology? Because you would realize that almost all the technology that we use today, like the radio, sending a rocket to Mars, everything uses Maxwell equations and Newton's laws, and nothing more. And if you look at optical fiber, communication, what we do today, our present day computers, they all rely on, simple, Maxwell's equations, manipulation of voltages, and Newton's laws, nothing more. But, as you will see, in say 60s and 70s, when the chip size became smaller and smaller, there was a demand for making computers smaller. Very quickly in 70s, they realized that the computers are heating up. As the size is becoming smaller, the computers are heating up. As we know, for example, whenever we have resistance, current passes through it, it heats up. After some time, there was problem because of heating, information was getting lost. And then, suddenly there was a lot of noise. Why there was a lot of noise? Because, what are these chips? They only, collect electrons at the basic level. Everything is quantum. So when the, size becomes smaller and smaller, quantum nature manifests. So therefore, the quantum effect was indirectly manifesting in terms of heating, noise. So in 70s, and computer science people really encountered this problem. Some very beautiful ideas. For example, if you read Landauer, 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 a computer scientist person who really understood that heat loss is nothing but information loss. So this thermodynamics of interpreting everything in terms of information really came through the practical realization of engineers. So therefore, people started looking at quantum. And as usual, it was Feynman, 1982, the year I started my PhD. So he came up with this idea, and of course, he was trying to solve strong interaction, theory of strong interaction. Inside proton, quarks are there, how they are bound, a very difficult problem. It is this million dollar problem. If you solve it, you will get $1 million. Why, for example, inside proton, quarks are there, interaction is so strong, you cannot remove them. Look at, for example, hydrogen, you can ionize, you can remove electrons. From here, a rocket can go to Mars, so Marses can leave. But why this interaction of which, of course, through nucleus is so strong? We know quarks are there, we see them through experiment, you cannot come out. While looking at problem, Feynman realized that you need a quantum machine to solve a quantum problem. Because try to simulate the so-called lattice gauge theory using standard computation, there are limitations. So then he came up with this beautiful idea that why not use a quantum machine, so-called quantum computer, for solving quantum problems? His thing was not for technology. Believe it or not, a fine person like Feynman had difficulty in publishing the paper. So finally, this International Journal of Theoretical Physics, which was a new one, that editor met Feynman in some conference, and Feynman showed him the paper. He said, why don't you publish in my journal? So first paper, non-trivial paper, came out in International Journal of Theoretical Physics. So then, the people who were thoughtful, they were already into it. In USA, particularly in America, these people who are working on quantum foundation, they were all. Hello? Somebody is talking. Somebody's voice is coming.
Sarah.
Yeah, Sarah. Sarah, can you switch off your microphone? Anyway, right now there is no voice. Am I audible? Sunita, am I audible?
Yes, sir. Yes, sir. You are audible, sir.
So therefore, in 80s, the people started looking at this quantum mechanics from the perspective of technology, computation. What are the basic limitations in a classical computer? People really started looking at in 80s. And I was doing my PhD those days. Believe it or not, anybody was working on foundations of quantum mechanics, they were considered as nerds. These people who have nothing better to do, this Bell inequality, foundations, those things were considered not very great things those days. So most of those people did not get jobs. They went to colleges or in some small companies. One of them was Wooters, very famous man. If you saw Wooters, Wooters. And this person called Jurek, Zurek. Jurek was fortunately in Los Alamos. He was doing something else because of which he had a job in the famous Los Alamos lab, which created the atom bomb, and simultaneously doing this. So they looked at it. What is the basic difference between quantum and classical? One thing they found that no cloning theorem, 1982. You take, for example, a quantum state. If it is not known to you, you cannot clone it. Xeroxing is not allowed. So you remember that there is a theorem called no cloning theorem. Whatever technology application you cannot Xerox. The idea of giving some paper to a student without knowing Xerox it, that is not available in the quantum world. Jurek and Wooters, those days very famous result, but nowadays only we came to know about it. I didn't know about it. Then other limitations, that information cannot be sent faster than light. That of course relativity has taught us. You cannot delete a file. Once you have created some file, you cannot delete it. Quantum no deletion theory. So slowly, a lot of things in 80s, people realized that quantum computer will have problem because of these kind of things. Now then came David Joyce, very famous man. He gave a very beautiful thing. Englishman. So he said, suppose if you want to do a quantum computer, So he designed it like classical electronic circuit. If you go to electronics thing, you will see circuit diagrams. Exactly same thing. Like regular computer gates. Most of you are into technological kind of things. You know this NAND, NOR. I am not very familiar with them. These gates are there. So in a regular classical computer, you draw these lines, draw these gates, and there will be a register through which programming you do. Then there is the output, you read it out. Same design he gave, I think around 84. So he pointed out very beautifully that certain this NAND gate is not allowed in a quantum computer. But quantum computer gave enormous simplification. Only two gates are enough. So he proved universal quantum computation. Only two gates are enough to do any work in a quantum computer. Again, the paper was not accepted in mainline journals, same International Journal of Theoretical Physics. So some of you who are curious, please read these two papers. Richard Feynman, 1982, International Journal of Theoretical Physics. David Doyce, International Journal of Theoretical Physics. And so this idea of a quantum computer was born largely due to these two gentlemen. And then properties of, that what kind of gates you can design, all those things came by study of, with foundation-oriented people, quantum foundation. Those are looking at basic aspects of quantum mechanics. How true is quantum mechanics? What are the puzzles in quantum mechanics? Those people discovered this no cloning, no deletion, no xeroxing, all those theorems. They were finally gotten into designing of a quantum computer. The 90s, so basically what I'm telling you, in 70s, engineers encountered problems in terms of circuits heating up, information getting lost, noisy kind of things. The physics people were trying to solve big problems. They encountered, like Feynman and many others, that a quantum computer could be a better thing to do because a quantum can tackle a quantum very naturally. Then universal quantum computation, David Doyce. So these are the development of 80s. And I remember, I first joined in City College of City University of New York in 1982. Our quantum mechanics teacher, Greenberger, had a lot of hair, white hair, always jumping up and down, foundations of quantum mechanics. All of us used to make fun of him. But those days, there was this gentleman, Zeilinger, who was visiting City College, and he was a nuclear physics person, didn't have a job, was a postdoc there. They had another visitor, Horn, Greenberger, Horn, Zeilinger. And without us knowing, they designed and they showed a state, quantum state, which was very interesting, because of which their name is now written in history, GHZ state, Greenberger or Zeilinger. And believe it or not, we never knew about them. Zeilinger is now Austrian Science Academy president. All the revolutionary experiments in quantum computation is being done by him. And he was there, we never knew about him. Our heroes were Michio Kaku doing string theory. America was, strong interaction, grand unification, string theory. Nobody knew about the developments which is taking place parallel, which is now coming into reality. So then, 90s, there were again two revolutionary things. That was that, this Peter Shor, again computer scientist, engineer, he showed the factorization can be done very fast in a quantum computer. So-called, polynomial time. Computer people have tasks in terms of hard problems, NP hard, different kind of things. I'm not very comfortable with them. All I know that it takes a lot of steps to do so that in your computer you cannot do it. Then this person, and based on that, you have, cryptography. Certain things you do, like for example, factorization. You can simply design a cryptography protocol using factorization in a very simple way. So he showed that a quantum computer can factorize things very fast. So I think 1994, and that immediately there was alarm bell ringing, where Swiss Bank and CIA. Those after that, this quantum computation came into mainstream newspapers. I remember 93, I left USA. Those days, people are beginning to talk about these kind of things, that factorization, those things. People are beginning to hear. I also heard about it. So then, Indian person working in IBM, Grover, Locke Grover, LUV, very nice gentleman. And he came up with this thing that if you're looking for search algorithm, like Google search algorithm, He said a quantum computer will be the fastest. He proved it. And you are looking in the library for a book, so-called unsorted search. If you have a quantum computer, you can do the fastest. That received a lot of attention. These two in 90s, that you can actually do quantum, quantum computer is required. It has advantage and it will be useful. That these two papers actually brought into the mainstream. So money started coming and experiments people started doing. Who are the people who did experiment? This nuclear magnetic resonance, NMR. The very powerful NMR machines available all over the world, including in India, Professor Anil Kumar in IISc. So they were looking for very small signals in biology, molecules. They naturally turned into doing quantum computation. In fact, to a large extent, even now, most of the results are coming from NMR. Slowly, NMR, you cannot make it a big thing. So therefore, light-based, microchips-based quantum computation is now coming, but even now also good results are coming from this biology lab kind of thing, which require NMR, nuclear magnetic resonance. Therefore, you can see in late 90s, most of the results are coming from NMR machines. Now, what kind of results? The computer people, as I told you, Landauer and others, they really computer people, they face problem because of heating. Then they started looking at alternatives. So most of the quantum revolution was led by the engineers. So in late 70s, there are these two gentlemen, Toffoli and Fred Keane. Fred Keane was in Caltech, Feynman's friend. So he realized that heating is taking place because it is irreversible. You see, loss of information, entropy, thermodynamics. If he can design a gate which is reversible, then there will be no heat loss. In fact, a design, it's called Fredkin gate. Now it turns out that that is actually like a unitary matrix. Quantum mechanics uses unitary matrix. So he, without knowing, he designed a reversible thing like Toffoli gate also. And those are all reversible. Now we understand that why there is no loss of heat, why they are reversible, because they are so-called unitary matrices. They don't lose any information. Quantum mechanics is basically mechanics of unitary matrices. But computer people are smart. They understood that and they used it. So Fredkin and Toffoli, these two gates came out from computer science people who did not want heating and loss of information. And the physical meaning of that came much later. In 90s, there was some very interesting development, largely due to there was this guy Wisner, a BSc student in Brown University, I think Brandeis, if I remember correctly, Brandeis in USA, and he was taking an undergraduate course of quantum mechanics. There the teacher pointed out that in quantum mechanics, there's a basic difference from classical mechanics, that if you are experimenting something, you will change the state. Classical mechanics, suppose I'm looking at something, I'm not changing the state. I see the glass is glass. But in quantum, if I try to see something, it will be changed. That is how Heisenberg argued about the uncertainty principle. So when uncertainty principle was explained to him, that quantum mechanics, the observation changes the state, the very basic difference between quantum and classical, he realized that it can be used to create money. Money which is foolproof, which you cannot forge. The moment I will try to forge it, then the person who has created it would know, because forging is an act of observation. Therefore, it will leave a signature. So he came up with this concept of Wisner money. But he was a dreaming undergraduate student, never ever, could make the idea mainstream. In 80s, early 80s, he met with Bennett and Brassard. They were the people who understood their idea. And they said, why don't you write something? So that Wisner money was written up. In between, these two gentlemen, Bennett, who was the head of computer science in IBM, Brassard, who was in University of Montreal, who is still there. In fact, I was a postdoc in Montreal in 92-93. I have heard several talks from Brassard. They came to Bangalore. There was a conference. Over this beer, they came up with the application of first application of quantum mechanics. using this idea that measurement changes the state. It is called quantum key distribution, QKD. If you give a search, that is where the research is going on. QKD machines are available. Why you need QKD? If you remember, this OTP protocol. Through OTP, we get a number. That is our key. Quantum chromodynamics QKD does the same thing. Through quantum mechanics, generates a key for you that can be used for secret, your secure, transmission of information. So in banks, for example, they depend on that. Everybody depends on that. Through OTP, we also depend on that. A secret number, good number has to be generated, which is personal to you. You can use it for transmitting your information. They found this very idea, which Wisner used to make his money, that quantum mechanics, the process of observation, changing the state, can be used to create a secure key. How is that possible? Basic idea. Alice Bob, they want to generate a key because they want to talk to each other. In between, Eve, the evil lady, wants to put her ear and hear what they are talking. Whenever she was to hear, he would leave a signature, so they would know. And believe it or not, it's exactly based on this, that observation changes the state. QKD was idea came in Bangalore over beer and was published in a proceedings from Bangalore. First real application of quantum mechanics is an idea that came from Bangalore and published in a proceeding from Bangalore. So then in the 90s, this Wisner, who knew physics, Bennett, Brassard, were engineers, computer scientists, they all got together. They had about the EPR paradox, which I will be talking very briefly. Einstein, Podolsky, Roses. When quantum mechanics came, Einstein was bothered by this thing, that measurement changes things. They're saying that God cannot be playing dice with the world, right? Everything will be uncertain. The moment you measure, you change things. There must be some, hidden variable which is doing all these things in a very deterministic manner. He was not very comfortable with the statistical interpretation. You measure, it collapses. Collapse, which Niels Bohr and his school gave from Copenhagen. That measurement changes the states collapse. That hypothesis he did not like. And he may said in many ways that there should be some local reality, there should be some realism. So Einstein EPR paradox was born in late 1930s. And it remained as a paradox. It bugged people all over, even now also. But these two gentlemen, these people, Wisner, and all these people, they got together, they used it. They used it for which purpose? Teleportation. That you must have seen in Star Trek movies, you can teleport. So teleportation was the idea, a beautiful idea. If you work it out, even now when I work it out, you can send an unknown letter or unknown state from Alice to Bob, located in Earth and Mars. Or for example, right now, in Beijing and Austria, Vienna, which has been done recently through satellite. You do not know which state you are sending. The fellow does not know who is receiving, and it goes exactly. It is teleportation. So that experiment was done through NMR in late 90s. First idea of using this unnatural effect of quantum mechanics through a paradox to come up with a technology called teleportation came in 90s, and that really opened the floodgate. This experiment was late 90s. So this quantum chromodynamics, teleportation, these are the major things going on right now. You must have seen in newspapers. QKD machines available. There are farms producing quantum QKD. These machines. Right now, for example, if you go, almost everywhere, this secret transmission is going through this, including our own Prime Minister's office, defense, USA, everywhere now. And the first thing was used in this 2010, I think, that South Africa football final that was secured through a quantum QKD protocol. If you see, first application, mass use of it was in that South Africa, final World Cup, World Federation, what is that, our football final. So therefore, now banks and many of these people, they use this QKD apparatus for secure communication. Teleportation has not come to market yet, but experimentally across the continent, from China to Vienna through satellite, it has been done. So technology quantum random number generator. Again, the same thing, that the moment you touch a quantum state, it collapses. And it is arbitrary, so-called collapse of the wave function through measurement. Very simple idea. The basic difference between quantum and classical, that has given all this technology. It has been used to generate random numbers. You can check. If you look for random number, like you engineers knew for your MATLAB, when you slash rand, that generates pseudo random number for you. After some time, you repeat. But USA, for example, is now broadcasting openly random numbers generated through a quantum computer. All these things through a very, very fast basic principle of quantum mechanics, that measurement affects the state, it leads to the collapse of the state. All the technologies are only from there. Next thing about quantum is something called entanglement, right? That which led to the so-called EPR paradox. People are also beginning to use that now. So now people are using these kind of things for technology purpose. So now let me go very slowly. You can stop me. Quantum computation and technology. Okay. What happened? Yeah. So who are the heroes? As you are familiar, Heisenberg is the main person. Very young man, 1925. He had a hay fever. He dreamt about quantum mechanics in a state of fever. Realize that matrix is a thing. The basic difference between quantum and classical is that quantum mechanics uses matrices. Before that, people use matrices, solving linear equations. All of us do in high school. But the quantum mechanics uses matrices, and quantum mechanics is matrix mechanics. That realization came to him. So he suddenly remembered that his teacher has taught him, and he has taken a course of quantum mechanics, matrix mechanics. And that matrix is the thing which he used. And he was from Germany, so a group of people in Germany, Max Born, Heisenberg, were interpreting quantum mechanics, Jordan. They thought that the paradigm shift, classical and quantum, very different. Classical world, Newton's law, differential equation, you solve it, right? Mx double dot, right? Actually, mass times acceleration is equal to force. Force is derivative of the potential. So these are all, local laws. So they thought that matrix is very different. Lo and behold, when they are basking with this new paradigm shift, there comes two papers from Vienna that same summer, showing that quantum mechanics, classical mechanics differ by one small step. So-called Hamilton-Jacobi, approach to classical mechanics is very, very close to quantum mechanics, and not only that, he uses it to solve hydrogen atom spectrum, that the energy levels goes like minus 13.6 electron volt divided by n square. If you read that paper, very readable paper, and Schrodinger probably was one of the very smart person of that era. He has written a very beautiful book about life, what is life, and just one step which takes you, and that stunned the Germans. That is it really so, and it is actually so. And this silent person, Dirac, Paul Adrian Maurice Dirac, he had come to Niels Bohr's Institute. Dirac was a very, a person who does not talk much. And Bohr was very unhappy with him, that he thought people come to his center to discuss, but he will always stay inside his room, work out on the blackboard. Very quiet person. So Niels Bohr thought that, he is a person who doesn't interact. Then suddenly, once he saw that there was a long tree. So Dirac looked around when nobody was there. He, with coat and tie, climbed the tree. Then Bohr was very amused, because Bohr was also a very unconventional person. So those days, Copenhagen was the place where Niels Bohr used to host a lot of people like Landau from Russia, Dirac from this place, Enrico Fermi from Italy, Niels Bohr, was hosting all of them. Heisenberg, all these people used to come there, discuss ideas, and come up with a lot of revolutionary things. One contribution is Copenhagen interpretation of quantum mechanics about measurement. That measurement is arbitrary, leads to collapse of state. Between Einstein and Bohr, there was huge debate. Many of you might have read it already. So Dirac was a very silent person, but he really understood the basic aspects. His book in 1932, even now, is exact. One thing introduced, a single photon can interfere with itself. That really changed. That means photons are actually waves, one photon can be in a wave such that the wave can pass through two slits having one photon and interfere with itself. That a single photon can interfere with itself. That idea was due to Bohr, so due to Dirac. Right now, for example, that really introduces quantum mechanics to common people. That is very different. Then Louis de Broglie, who realized that it is not only light which Dirac used to explain this thing, electrons also behave in the same way. We are using that now. All the quantum computers are using electrons because photons are not easy to handle. But Dirac really understood, he formulated quantum electrodynamics, basic ideas, and path integral formulation idea was also there, if you see, which Feynman carried to its logical end. Now, so he is also one of the heroes. All right. So this is the equation. You don't have to know, the people who know it, this is the notation. Ket, bracket forming a number is due to Dirac. This is called a ket. And in the coordinate space, it becomes wave function. This is time evolution through Hamiltonian. Hamiltonian was known in classical world, energy. That is how, through Hamilton's approach, Schrödinger pointed out that there is only one small difference. You take the so-called Poisson bracket in classical mechanics to a commutator. XP Poisson bracket, which was 1, becomes I times h bar. That's all. There's nothing more. Poisson bracket has same property as a commutator. It becomes I times h bar. Okay. So, very small difference. Now, you can do then this, Heisenberg by that time was using operators. Remember I told you about matrices? He was actually dealing with operators. They are matrices. They don't commute with each other, as we know, matrices don't. So that was his picture. And Schrödinger had his picture where wave function represented everything. And it was, many people like Maxborn, Jordan, Dirac, who pointed out that all these pictures are same. All right. So now Dirac actually then pointed out we can use it, both of them, very nicely if you're dealing with realistic systems where there's interaction. If there's interaction, you can make the wave function part of it is time dependent. The part which you don't understand, you keep it out, and you can actually interaction very nicely can be dealt if you combine them together. So this is the picture which emerges everywhere. First, Newton told that light is particle. Huygens said they are waves. Both the sides there was support for 50 years. One concept will survive, another 50, another one. Then finally, Louis de Broglie pointed out that both have in quantum world, both of them are true. This. Since then, people have been talking about all sorts of things, trying to imagine that it is like a wave on which a particle is riding. So that is also another picture, that pilot wave theory of Louis de Broglie, that there is a wave on which a pilot is a particle. So there are many different kind of experiments people are now doing with the advancement of equipments to check out many of the ideas. Nothing much has been ruled out. Many pictures of quantum mechanics is there, but so far all experiments have seen collapse of the wave function. The moment you try to measure, the wave function changes. It collapses to the state which you are looking for. So the statistical interpretation of quantum mechanics, that actually bogged many people. If people ask, if I do an experiment, I'm going to change it. So what kind of computation I can do? But amazing thing is you can do computation and you can do certain things faster than a classical computer. And can you do everything faster? Answer is no. The best possible way is again hybrid. Combine both of them, possibly you can have a better one. All right. So in quantum mechanics, this Hamiltonian energy is the main thing. It makes you move in time, develop in time. Okay. So now, as I told you, the EPR paradox was the one which spurred technology, debate, led to basic understanding of quantum mechanics. What is this EPR paradox? As I told, there are these two particles, Alice and Bob, two parties. Okay. It could be a particle decay. It could be like, for example, if you take a meson, pi naught, or exciton, for example, if it decays, two photons come out. One is seen here, one is seen here. Okay. So, but both of them have come from the same source. So they maintain some kind of correlation between them. For example, if you take hydrogen molecule, you will see it could be para or ortho. So the two electrons could be in spin 0 state or spin 1 state, ortho and para. So when, one electron comes out and is measured here, other electron goes to a definitive state. You can see that now. That, if you take hydrogen, you find the lowest electrons are two of them are in singlet state, spin 0. But electron has spin half, the other electron has spin minus half. If Alice sees half, Bob will see minus half. If Alice sees minus half, Bob will see plus half. How far they are doesn't matter. This is the correlation which blocked Einstein. That how is it possible that they are able to maintain this kind of correlation so far away? This non-local quantum correlation is the key to many quantum technologies. So as I told you that measurement leading to collapse of the state is one key. Teleportation is another thing people are seeing experimentally. And that too now across the river Danube in optical fiber up to 500 kilometers through satellite between Beijing and Vienna, many places. That uses this kind of correlation, non-local correlation. But what Einstein got blocked became technology. So this, this aspect, this correlation, also blocked people like John Bell. He used it to show that there is a quantitative difference between the quantum world and classical world. He really made it quantified. If you measure something, if it is below 2√2, some kind of some objects if you measure, then it is classical. If it is above, it is quantum. And it was found experimentally, starting from Rochester, where I did my PhD during that time. Alan Aspect is the person who did the experiment following up from Rochester or the 80s, and quantum mechanics is always right. Even now also people are doing more and more careful experiments. You see this Bell state measurement, so many things people have taken into consideration. Human consciousness, and somebody has not used really random things. So even now also more and more sophisticated experiments. Like 2019, they did a paper in Nature, and to check that this quantum thing is correct or not. Is there any subtle thing like human choice is affecting it? So many beautiful experiments. I'll show you some of those experiments. People have gone to great extents to test quantum mechanics. Okay, for example, this experiment, I would not, this is basically a simple idea that two things must come out from one source and they get correlated. You can do it through light. This kind of thing denote a detector. So you can see the kind of sophisticated experiments people do. This just to show you. So now what is mathematically? As I told, Alan Aspect is the person still alive, doing very well. He came to Calcutta. Okay. Now, okay. Now this concept of maybe, that yes, no, maybe, that is, as I told you, if you measure this state half, the other will be minus half. If this is minus half, the other becomes plus half. If somebody asks you, what is this state? You can always say it is probably half, or maybe it is minus half. So this logic, yes, no, maybe, that the linear superposition of yes and may existing leading to maybe is quantum mechanics. That is linear superposition, which pictorially is here. So then people asked, where have I seen linear superposition? Answer came vectors, just like Heisenberg discovered matrices. People realize vectors are where I have seen. A plus B you can add. So as now everything got translated into language of vectors. Matrices, of course, use vectors. Matrices themselves are vectors. So matrices and vectors. We know vectors. All our science people, first year we read vectors, A plus B, addition of vectors. We are looking so complicated, that you take this A, you draw this thing, and best thing was to take it components, add them component wise, magnitude of a vector, all these things which you use. Because force is a vector, velocity is a vector. That is the language of quantum mechanics. People discovered very quickly. Vectors naturally allow you superposition. You can take A, you can take B, you can get A plus B, or you can take A times B plus, A dot B, that is, and A mod square. All those things became the language of quantum mechanics. Believe it or not, nothing more than that. So Bell's inequality is in terms of probability. You don't have to get into it. Main thing is if you do certain measurements, you will get a number called 2√2. If you get above 2√2, it is quantum. And they have seen that all the time. So it is this word local realism due to Einstein. Okay, so as I told you, one to rule out human choice and that people are not affecting each other. 1 lakh participants were taken in the Barcelona experiment, 2016, and 12-hour period separately, 13 different kind of experiments checking it came out in the nature. And since then, there are more and more sophisticated, experiment people have done to observe this kind of correlations, which is non-local, to rule out, that it's not due to any other thing like human choice. Okay, many very sophisticated arguments have gone through all over the world. People are doing experiments. One result is that you going to use it. It's not that the machines which have come out to check these things are becoming technology. So that is the idea. That for example, now China is taking the lead everywhere. All the quantum communication is China is the leader. I'll show you most of that. This person called Pan, J.W. Pan is the leader. His teacher, Zeilinger, is in Vienna. So many of the quantum communication is taking place from China to Vienna, Austria. Okay, so now, when I started, this thing, I looked at the so-called Bell state. These are nothing but matrices. You can see here what kind of matrices. Where is that matrix I wrote? Yeah, you can see here. This is a matrix product. 0, 0 is a matrix product. So these are matrices. As I told you, superposition, addition of vectors. These are vectors. As you know, column vectors, to be more precise. If you see, this is a column vector, this one, for example, is 1 by root 2, 1, 0, 0, 1. 1 by root 2, 1, 0, 0, minus 1. These two are 1 by root 2, 0, 1, plus minus 1, 0. When I saw it, I was amazed. They are the 4 states, just matrices. They may arise by solving linear equations, 4 by 4 linear equations, like for example, Ax plus B is equal to 0, Cx. And you get this kind of thing. So what is so special about this? They are the so-called maximally entangled state. All the things which Allen aspect measured, all the inequalities only come out of here. So I used to ask everybody when I was in Ahmedabad Physical Research Laboratory, whomever I used to meet, I'll ask them, just tell me what do you see so special in it? And finally, believe it or not, one engineering student one night at 3 o'clock called me, sir, I know what is so special about it. So then he actually pointed out there is something very special about this column vector, which is making it maximally entangled. What is the meaning of that? I'll show you. Now, therefore, and another thing what bugged me is this, you maintain these kind of things you are using for technology. Now, as I told you, the moment you do the measurement, the state will collapse. It will go to 0, 0 or it will go 1, 1. Entanglement is gone. So what is entanglement? You see, if it is a state like 0, 0, you can factorize it. You can write 0 times 0. Alice has 1, 0. And what is this 0? This is called qubit. It's a column vector, 1, 0. Difference between a classical and quantum computer is a classical computer uses 0 and 1 numbers. Ask them 0 plus 1, 1 plus 0 is 1, 1 plus 1 is 0. So this mod 2 mathematics, addition mod 2 is the language of a classical computer, nothing more. And according to them, this 0 is no voltage. You take a chip, if you don't apply voltage, that becomes 0, number 0. Apply the voltage, that becomes 1. And that is how the manipulation takes place. Numbers addition mod 2. Quantum replace that 0 by something called qubit, a column vector. For people like us, it's a column vector. 1, 0 is 0, 1 is 0, 1. They are vectors, simplest vectors, 2-dimensional vectors. Add them, you can subtract them, you can find out the magnitude, you can show their orthogonal. Like, for example, I, j, k unit vectors in 3 dimensions, they are orthogonal. I square is equal to 1, j square is equal to 1, k square is equal to 1, I dot j is equal to 0, because they are 90 degrees between them. Same thing here, 0 and 1 are orthogonal. They form a complete space. What is the meaning of complete? In 3 dimensions, you need 3 unit vectors. In 2 dimensions, you need 2, 0 and 1. In 4 dimensions, you need 4, these 4. So, language of quantum mechanics is matrix. So all this matrix multiplication, matrix operations, everything quantum mechanics uses. Only thing that is new here is measurement. You take the state, it's a linear superposition called maybe state. If you measure Alice here, Bob here, if Alice gets 0, Bob will get 0. If Alice gets 1, Bob will get 1. This nonlinear correlation is the one which is EPR paradox. So you can think about this, why this state is so famous. All the quantum paradoxes comes out of this column vector, 4 of them. Now, when I started my life in Ahmedabad PRL, suddenly our Professor G.S. Agarwal in Physical Research Laboratory started a division, quantum optics, quantum information. I was made overnight head of that division. So I asked Professor Agarwal, is it a joke? He was very annoyed. He said, what do you mean it's a joke? I said, I don't know quantum optics. He said, you have your PhD in quantum electrodynamics. Then how about quantum computation? He said, do you know quantum mechanics or no? I said, yes. He said, nobody in the world right now knows. So all of us, let us start working. And he himself started also. So there was this engineering student, Manu Gupta, now working in Jalandhar, engineer, electronics. He was coming, visited us for 6 months, worked with me. First thing, being an engineer, he was balked by this. That if I have, a state which is entangled, you tell me that the moment I do the measurement, the entanglement is gone. Suppose I have a computer, and suppose I have given a problem to solve it. Now, if in between, because of this environment, the so-called decoherence, or somebody trying to, look at the state is gone. How do I know my computer is working or not? That is how we started our life. This entangled state is here, this one. 2 of them. Therefore, we got into the electronic language. I used to hate electronics, but I found this the best language for quantum computation. So this is a quantum state represented by a line. As time progresses, or you can see it as an architecture, this could be X. This kind of 2 objects joined together by bracket is an entangled state, which is psi, means Bell state. So Bell state is part of a quantum computer. I want to check if the circuit is working or not. I put another line parallel to it outside. So David Doyce has taught me that quantum computation can be done through 2 gates. One is called Hadamard, which is acting on 0. Another is called control not. You see, this flow is controlling this is the notation. And I can extract information. I can read out the state by doing the measurement. So all the circuits what I need for any design of a quantum computer, universal quantum computer is here. Hadamard is a 2 by 2 matrix, 1 by 2, 1, 1, 1 minus 1. Control not joins is a 1 party controlling the other, 2 party operation, single party operation, control not. What is control not? If, like in computer science language, if 0, 0 is there, it will not change it. 0, 0 will remain 0, 0. 0, 1 will remain 0, 1. 1, 0 will change to 1, 1. 1, 1 will change to 1, 0. If the entry is 1, it will change, otherwise it will not change. In terms of matrices, it's a 4 by 4 matrix. I did 1, 1, 0, 1, 1, 0. That's all. This arrow is for measurement. Any circuit you see, you will see this. Only this. Universal quantum computation can be done only using it. You can make it a little more, thing control Z, other kind of things to make it faster. But everything can be done through this. What I am showing here is that through this measurement, you can actually read the state. And at the end of the measurement, the state is intact. You got psi, you have psi. You know the state is there or not there. So we wrote this paper. The moment we wrote this paper, immediately, there are quite a bit of responses. But to our good luck, Professor Anil Kumar, the leading expert of IISc, NMR, he did this experiment. Of course, a bit more later when Gupta was there in Bangalore working for a software company. He went there, met him. He did the experiment and showed that it is indeed possible to do it. And that now people are using for many things. And to our good luck, Professor Anil Kumar's real student, Jharana Rani Das, did it. And it's a sad thing that she had lost her life in an unfortunate incident. So this paper, Jharana Rani Das, Gupta engineer, myself, Anil Kumar, is in Journal of Physics B, and you can actually show that a quantum computer can be checked without altering it. So now, these NMR people, what they do, their state is actually a very noisy state. They call it pseudo pure state. From there, they have actually way of extracting information. So I will not get into it. Typical language, you will see phase and parity. What is phase? Plus minus is phase. Parity is 0, 0, 0, 1, 1, 0, 1, 1. That is called parity. If it is 0, 0, 1, 1, the one parity. 0, 1, 1, 0 is another parity. If you see here 0, 0, 1, 1 and phase is plus minus. This information is there. That has to be extracted. It is extracted measurement by an outside state called ancilla. So this, I'm just trying to show off to you that typically the spin kind of Hamiltonians are used everywhere now. IBM quantum experience, which is existing, it uses the same kind of Hamiltonian. Spin in single particle, two particle. So this control knot can be done through these two particles. Because I need an ancilla and two other state, three spin system is there. And this three spin system is derived from the most favored molecule. All over the world they use it, chloroform. That's the reason people make fun of them that did you really see it or chloroform affected your brain? Amazingly, chloroform has provided the molecule of choice to do quantum computation. And it was also done using chloroform. All right, so they have their NMR, the states how to prepare. You start with pseudo pure state, prepare them by giving, in the commands, radio NMR commands. Then you ask your question, that is your encoding, phase and parity, and then you read out. Finally, you see, read out, and then you draw them some nice pictures, and that you really saw it. So these four stages you do. Everywhere, evolution is unitary, except measurement. So this Hadamard gate, and through that unitary evolution, you can do control knot also. All those things can be done. Typically, you will see these kind of things. And as I told you, John Asma, this is the paper, 2010. All right. So now people become. So as I told you, this Bell state is very, not very robust. The moment you expose it to environment, just like something buildings rust, irons rust, you want to produce things which will stand the test of time. You have to go for more sophisticated things. Bell state very easily gets corrupted. The moment some heat is there, state is gone, which is called decoherence. So Bell state decohere very fast. Quantum computers are major problem is decoherence. You have to create something which is very robust, which should not be affected by heating, should not be affected by the environment. So decoherence, creating error, correction of error, you can check out, is a major occupation right now. Now, whatever machines have come out in the world, like field access to you, like IBM and D-Waves, they're all affected. Noisy circuit, very noisy, very quickly. But when using that, people are able to do it. So error correction, noise removal is the major occupation right now. Most of the quantum computers, almost all of them are very noisy. All right. So how do you produce states which are not less affected? I'll give you an example. Hypercube state created 2019. You come up beautiful geometry. What I'm plotting here is the so-called Wigner function. You see, because of this interference effect, looks like the states are all tightly bound each other. You try to change one fellow, the other fellow will resist. And because of this tight bonding, the state is actually very robust against environment. And it's produced through light. These are the kind of things which people are using it now, beginning to use. So finally, again, silicon and light, they will be the point. Fortunately, I am part of a collaboration. This is called Hypercube. I am part of a collaboration, Indo-Italian project with Professor Urvashi Sinha in RRI, Dipankar Home and Good Prasad Kaur, big names, quantum information theory from Calcutta. Professor Home is from JC Bose, and Professor Guru Prasad Kaur is from ISI. And Calcutta has been the place where a lot of, these foundational aspects of quantum mechanics has been going on for quite some time. Very, the large number of people working on quantum information, good number of results have come out. So with them, we are the three theoreticians. Urvashi Madam is the experimentalist, and there is a collaboration with Italy. So the chip is now being produced there. In fact, they have already produced it, silicon and light. So that thing will be coming to Bangalore. So India will have a chip, hopefully in a year. So this collaboration. So light and silicon, good old silicon. That is the one the world is going to rely on. Present day quantum computers are designed to superconducting qubits. You take superconducting units like in IBM. Superconductivity is a very nice quantum phenomena. So it's a macroscopic manifestation of quantum mechanics. Use those kind of things to design. So you can check pictures, but they're very, highly weight is very large, and they cannot be made very big, but they're better than NMR quantum computer. NMR quantum computers are huge, very costly, can't go beyond certain things. So light is the hope. You might have seen recently in China, there was an experiment where 500 qubits were created using light. Those pictures are fascinating, you see, but very big. But all your classical computer used to be big also. They became slowly small. Now, for example, that is what I was telling you: quantum teleportation, ground to satellite. So 1500 kilometer ground to satellite. This is, I think, Tibet to the name of the satellite is Mischief satellite in Tibet, from the city in Gari and Tibet, 500 kilometers. 6 input states were sent. Fidelity means how good it was, 80% fidelity, which is pretty good. So through light. And you can actually check the name PAN, JW PAN. So there are articles in Nature saying that what PAN is thinking now. PAN was a student of Anton Zeidinger, studied quantum information theory, did experiments. When Zeidinger asked him to stay back, his point was, no, I'll go to my country, big, better machines than you. So his teacher, Professor Zeidinger, tells him very proudly that my student is doing better than me. But of course, Zeidinger doesn't give up. Austria is one of the leaders in this area. So now, people are now going from this qubit, like 2-dimensional vector, to 3-dimensional vector. So-called QT, angular momentum. All of you know angular momentum. If L is equal to 1, there will be 3 states. So people are actually using these things. Again, this Chinese group has taken the leading. They have shown they are able to produce them with good fidelity. You can teleport them also with good fidelity. Okay, so now these are the kind of light-based experiment. So this circuit is almost like your classical circuit. They do it deliberately because you have to talk to engineers, you have to talk to computer people. They understand this kind of language. So it's light, but circuit is on this way. You can check this. Zeilinger's group paper 2019. They produced this. And this PBS, what is that? Beam splitter, BBO crystal, right? Half wave plate, quarter wave plate. So these are the kind of optical elements which are used. Fiber, mirror, the same good old thing. Earlier you used to do, our experiments in optics lab using this in a classical domain where a lot of photons were there. Now you use almost single photon, 2 photons, and you have such control that you are able to read them. See this is an experimental paper. You see ancilla, input state, the readout. Here is the readout. The crystal is put here, and here are the steps which goes in. Source of entanglement is BBO crystal, the so-called type 2. Type 2, what is that? Beam or something, I don't know. Type 2 crystal or something called. You use basically, in crystals, there are these crystals which are birefringent. Okay, so BBO crystal is a birefringent crystal. The type 2 ones which are at once which generate entangled state, namely something like a singlet state, where one flow is 0, other flow will be 1. If this flow is 1, that other flow will be 0. And 0 and 1 are your matrices. And if you have 3 qubit, of course you have more states. How many are there? 1, 2, 3, 4, 5, 6, 7, 8 of them should be there. All right. So now, no, one second. I made a mistake. That in 3 qubit, you will have initially these 3 states. You see superposition state. And you see this, what kind of state? Very interesting state. You see omega square. You use cubic root of unity. Omega cube is equal to 1. So these states are created, they are orthogonal using cubic root of unity. And what is the reason? They are actually a very nice mathematical reality called, these states have a special name. What are the name? Maximally unbiased basis. Just like the English word means unbiased. They are not biased towards each other. So therefore, whatever you measure through them, you get an accurate picture. Maximally unbiased state. Okay. So now, QKD, quantum key distribution. As I told you, Bennett and Brassard, gentlemen, 1984. and it was done from in Bangalore. Now that is what now people are actually have made it a technology. People are selling machines, buying machines. So now only simple thing, measurement of single photon, and that is enough to generate security. Okay, so now variety of things people have used. This is the process, these are the measurement things, state of polarization. This stands for up and down, 45-degree, circular polarization, only measurement. And here the polarization of light. So, lot of photons are generated, measurement, and some telephone conversation. That is enough. And at the end, you come up with a set of numbers. Here, for example, 1011. This becomes your key. And it is a secure key because if Alice has done something here, Bob would know, and you discard that key. Okay, so 1984, and so now it has become satellite based. So now satellites, many people have. China, for example, these two. Now these are like components there. Now others also, Singapore has a microsatellite, Japan also has a satellite, and India is also planning to have one. Apparently, they are going to put a transponder. So you can check this group, Chinese group papers are available in the net also. 17, 18, 19. Once they put that mixture satellite, lot of experiments are done. Teleportation between us, China and Austria. Then entanglement preservation, checking that out, and many pathfinding experiments were done. This group, PANS group. Okay, so if you read, this kind of thing, what we are doing has not gone beyond first two couple of chapters of quantum mechanics. You don't have to go beyond. Therefore, if you read the first two chapters, know a little bit of matrices, you are enough. Therefore, you will see, I know if you are curious, take a look at some of my papers. In my Google Scholar, PK Panigale Google Scholar, you will see most of my papers are through young people because you don't need beyond very simple ideas of quantum mechanics and matrices. So one of those very profound idea is this Thorne-Gerlach experiment. You take 3.5 particles, you can actually put a magnet to defect them. If depending on the spin, plus half or minus half, you will get two components on the screen. Okay. Now this is the basic thing. If you decrease the number of particles, you will find out measurement will affect it. If one goes here, the other will not be seen. If the other goes here, it will not be seen. Similarly, if you take light, decrease the intensity, after some time, quantum nature will come out. So most of these things, what we are doing, can be imagined using only first two chapters of quantum mechanics. Okay, so now, and this many of the revolutionary ideas. For example, one idea to use a very interesting thing in quantum mechanics through this measurement called weak measurement is due to Aronoff. And how old is Aronoff right now? I think 95. Even now also is producing revolutionary ideas. Bohm-Aronoff effect, all the 60s. Weak measurement, people are beginning. And after Aronoff, it was George Sudarshan who showed why what Aronoff is telling is correct. Immediately after that, 1989. And this is called weak measurement. And people have used it using light, need not be in quantum mechanics. Very small weak effects, which are typically quantum, can be amplified using so-called weak measurement. Idea is due to Aronoff. And uses this kind of thing, Thorne-Gerlach experiment. Not very deep things. Now, this variable quantum eigenvalue solver. These are the algorithms, which people IBM is using, to compute energy levels of excited molecules. In fact, a lot of people have learned this thing. This summer, a lot of students from India were taught by IBM, and people actually, they know how to use it. Here the machine looks like pretty big, a lot of things to cool down based on superconductors. And these are the language, people are there teaching us to a skit. Students have learned, people have computed. For example, we have computed boron, hydrogen, ion molecules, bigger molecules also people have computed. So hope is that these kind of things will lead to better designing of drugs, and others predicts good prediction of molecular states, looking at the excited state dynamics more accurately. So you will see all over the world now, quantum computation has become an integral part in the chemistry departments. You see everywhere, Harvard, MIT, they are actually using it. And because they need accurate observation of molecular levels. Physics, for example, it is there in localized places. Engineers and chemistry people are using very extensively. Okay, for example, as I mentioned, our collaborator, Professor Urbasi Sinha, this is the Times of India article. To communication, they have a very QKD kind of thing, and they're part of ISRO. Through ISRO, they have got this funding. So the Indian Space Research Organization to have this quantum key distribution done between India and Canada. So their space agency and we, our thing, are actually collaborating to have a long distance thing implemented. So money has come now coming from 80. So many things, the government of India has a dedicated program called Quest, Quantum Inspired Science and Technology. Many of us have got funding. A theorist like me, for example, I'm going to advertise for postdoc and these things. Some around 800 crores they are given. Apparently, huge amount of money is there, which is going to come up and distributed very soon. The document, the theme paper is now ready for the next round of quantum, making the country good in coming up with quantum toolkits and quantum simulators and many other things. So there is an active program going on in our country now. And the first phase is Quest, Quantum Inspired Science and Technology. Next phase is the one which consultation and other things are over. Now soon probably it is going to be announced. Apparently in budget they have already specified 8,000 crores. So one of the things as I mentioned to you is drug molecule. You can actually find, sort of do these kind of things, and other quality drug designing is one of the areas where hopefully quantum computer will play a role. If you check, for example, the so-called D waves, just go and search D waves, you will find out. So they claim there's even a slightly different concept, adiabatic quantum computation. That they basically what they do, as I told you, there's a Hamiltonian. So they take the state, apply that Hamiltonian. It can do the quantum computation for you adiabatically. Adiabatically means you don't change the state too much because the states have to change. If there is no change, then there is no computation. Because the change should not be drastic. So it is not done through circuit. As I told you, Harvard, control lot, through circuits you can do, like IBM does. But D waves, the different concept, you feed in your problem, the Hamiltonian will evolve it adiabatically, and after some time you cool it down and read it out. It will give you the solution. So through Hamiltonian evolution, like NMR. That is the principle of D waves. For a long time, people did not believe that D wave is a computer. That led to a lot of queries, particularly for computer people, that suppose called quantum validation problem. Suppose somebody claims, I'm a quantum computer. How do you prove or disprove? That answer very nicely came from one Indian lady. I'll show you her picture very soon, Urmila Mahadev. That computer scientist, not even a physicist, I think, working with Professor Umesh Bhadirani, you can check, University of California, Berkeley, one of the very famous groups, by asking and measurement. So the same measurement-based statistics were used to prove that somebody is a quantum computer or not, quantum validation problem. 8 years, one paper. So now, as I told, who are the heroes? I have talked to them, this Grover's algorithm is one of the profound contribution of a quantum computation to the search algorithm. Log Grover, in his own language, he does not know quantum mechanics, he only knows 2x2 matrices. A computer scientist looking for a search algorithm born in a mirror. According to him, this log is for Lobkus. So Lahore, for example, has been named after love. That's what he told me. So this name derives from love. So now, database search algorithm. Claim is that it actually has been experimentally implemented. One of the things which is used everywhere now. Search algorithm, very, very good. During this COVID thing, and before that also, there are a lot of leading labs, like Oxford, for example, has a good leading lab. Now, different kind of phases people have seen. There's a problem called boson sampling problem. People are bugged about it. Because all the bosons are named after S.N. Bose, Satyendranath Bose. They are part of some Hilbert space called symmetric Hilbert space. So because of this symmetry, there is a sampling problem. People are bugged. Somebody who is curious can look at this kind of thing. So again, you try to solve it, through this kind of quantum computation, circuit diagram, create photons, photon pairs, right? Input state, readout state, detection, readout. Now, because of this quantum computer, people have come up with very good detectors, almost single photon level photon detection. So single photon detector is now a reality, partly because of this need. Now, how do you create entanglement? There are different kind of procedures. One is called heralding. If you do the measurement, if you find this state, that means you have created entangled state. So you put in some light, and these are silicon chips. You create photon pair. One fellow you detect, that means you heralded. That is called heralding. This is 680 nanometer, optical wavelength. So there are these stages. Put in light, and then photon pair you create. Through heralding, you know it has been created, and then measure the wavelength, and then you do the manipulation. That polarization state. Through Hadamard, control knot, you state preparation. After that, through polarization and time delays. For example, we introduce phase for you, because as you know, time delay means Hamiltonian will introduce some phase. That is what plus minus exponential I theta, the phase is introduced. The state is created, then you do measurement. So and readout. So these are the kind of circuits people use. Now, COVID-19 shutdown has helped quantum computation. For example, this error correction is one of the big things. People are really dedicated now, coming up with very smart algorithms how to correct errors. So this Eureka machine was working on without any problem, because electricity was not a problem, and there's no sound, not many people around. So you can actually. So they claimed that because of this COVID shutdown, Eureka was running all day, every day. Data never been excelled because of campus as a good, nobody was there. So, but thanks to that, their lab temperature was all right, and they could make the machine run for long time. So they could make some real progress. That's what they reported. Now, as our neighbor Singapore has invested on technology very early on, is benefiting harvesting the product of that. Center for Quantum Technology, that is their center. So and it has produced a microsatellite. They're actually looking for collaboration and largely with Indians. So many satellites are there. I've just given some pictures. Maybe I'll share this with you. Many satellites are coming up now. More are going to come. Acha. So, see, you may, sometimes when the students come to me, can I work on this thing? I always tell them that, you see, quantum computation has problems for everybody, because it is matrices, vector space. Sometimes our young people are much better than matrix multiplication, vector space, fitting patterns, which I don't do. But I have seen that. So this girl, Yun Tang, I'll show you your picture. I'll show you her picture is there. She went, 18-year-old girl, Yun Tang, went for her summer project, and was given a problem to solve. So the smart people from England, from MIT, Steve Lloyd, they have shown something a quantum computer can do faster. It's like a Sudoku problem. She showed a classical computer can do it better than that. She was only a high school student. Basically, because it is matrices, a problem like Sudoku, she could do it much better. It's not exactly Sudoku, a similar kind of problem. So if a high school teenager can do it, why can't somebody from here? And this paper you can read, Yun Tang, very low paper. Okay, so now, as I told you, that graduate student doing her PhD, the basic question that, are you a quantum computer? So 8 years, one paper, you can check in the web. That is the quantum verification problem. So two major problems, were solved by people who are basically using only simple ideas from quantum mechanics. Now, where are you now in terms of technology? You can check Professor Prem Kumar, very famous man, has a lot of money with him, around $14 billion. He's creating this net. First thing was from Ohio to Washington. He is in Northwestern University, electrical engineering department. So now people are, keep creating bigger and bigger line. China has a line, approximately 500 kilometers. Now, now many cities are going to put up this quantum network. So Calgary, for example, apparently has a quantum network now. University of Denmark Technical University has a quantum network inside their campus. So those things are slowly going to come up and are reality now also. So he works, see, Professor, he works in this Evanston area, Chicago. Look up his thing, he is a very good technology developer. Now, for example, you may say that people are talking about AI and other things. Where is quantum there? So actually, artificial intelligence is, quantum has its own version. So they are going to soon more machine learning. Quantum has also quantum machine learning. Those things will come up in a very integrated way. As I told you, the problem this little girl solved, 18-year-old in Tan, is called recommendation problem. So now I will not talk much about that. When she solved it, it's a picture. Okay, quantum recommendation problem. Need more about that is here. This is our Blackboard work. So now, all right. So basically, she used one algorithm by this Greek gentleman and Anupam Prakash from Cornell to solve it. That classical computer can do it faster. So now, actually, the point is that a good interfacing between classical and quantum can probably do much better, and that's going to be the one which will be used very effectively, because we are not going to do away with classical computer. It's not that the quantum computer can do everything faster. That's not true. All right. So now I talked about, Zeidinger is one of my heroes. I had the good fortune of being invited 2 years back to review Austrian science quantum computation progress in the last 4 years. So when I asked that how did they choose us, it was Steve Lloyd from MIT, myself from Philippe Rangier from Paris, and 2-3 other persons. They said that we have a AI-based package. We search for people who have broad experience, and then they bring the name to me. I select from them. So then he narrated that when he did his PhD, nobody was looking at quantum computation. He was in City College. They came up with this state, 0, 0, 0 plus 1, 1, 1. Anton Reininger comes to India. I used to come to India every year to meet with Dalai Lama to have a spiritual dialogue. Foundation, Australian Science Foundation president now. Very nice person. A lot of things he has done: quantum cryptography, quantum teleportation, entanglement switch, dense coding. And you may think that Yuan Tang is young, she can do things. Yes, we people are getting towards older age. I don't know, our hero, 95-year-old, still contributing. Everybody has hope, young and old. All right, so I think I'll stop here. I have taken enough of your time. Thank you very much. Yeah. Maybe somebody can ask questions now. How do I stop sharing? Sunita, am I done?
Yes, sir. Thank you, sir.
Yeah,
Sir,
yeah.
there was one question
Sure.
someone asked. Please elaborate hypercube state.
See, hypercube state is a state made using light. So first of all, you put light sources in a nice geometric fashion, and you sort of take the projection, a three-dimensional object projection on a plane. So there are some mathematical algorithm, like for example, you use this, building blocks, to make a tile kind of thing. See this, space with 5-fold symmetry can be created using 2 different kind of tiles. So similar kind of geometric idea was used. An amazing thing was that state which was created out of that projection on the plane of a nice geometry gave a highly entangled state. So that if one fellow is affected, the other fellow gets automatically affected. And to be very honest, I have not gone through the mathematics yet myself. So I'm going to read at it more carefully. It's a PRL paper which came out last year. If somebody is interested, we can read it together.
Good morning, sir.
Good
Thank you
morning.
very much. Sir, there is another doubt. Here in this PPT, you were showing that the young people, they proved that the classical computer is smarter than the quantum computer.
Yeah.
The previous slide. Could you
Correct,
show
correct.
that one?
Yeah. How do I go back? I go back. Yeah. This is the
How actually I didn't
See,
understand how.
it is not that a classical computer is better than a quantum computer all the time. That's not true. It is problem specific.
Okay.
The recommendation problem is the following problem. It's a matrix problem, okay, where the matrix
Mhm.
is a big matrix with low rank. If you diagonalize it, you'll find only
Okay.
few eigenvalues are non-zero. So it's a non-sparse. Most of the elements are non-zero. Non-sparse, low rank, large matrix. Some elements are known
Correct.
to you, other elements are unknown. Now, because it is low rank, there are a
Okay.
lot of constraints like in Sudoku. You can use that logic to fill up the blanks. That was the problem. So it's a matrix where some
Okay.
elements are missing, some elements are present, but the information to you was that low rank and non-sparse. So using those small things which are available to you, like in Sudoku, can you fill up the other blank places? That's what she did.
Okay, sir. Okay, thank you so much, sir. Sir, actually, I'm from electrical, and a lot of things which you explained was I couldn't understand. So, if you share your PPT or PDF, so
I'll
it
send
will
you. I'll
be
send you
better
the
for
PDF.
me.
Yeah, I'll do that. I'll send
Okay.
you the PDF PPT.
And
In between,
sir, can we email you if we have any doubt or anything?
always, no problem. Email to me and
Okay,
I'll
sir.
tell you this one. And
Okay.
yeah, sure, no problem. Yeah, thank you.
Thank you so much, sir. Thanks.
How do I get up?
Participants, any other queries? Thank you, sir. I think no other queries are there.
I'll now log out. Yeah, now go out.
Sir,
Yeah, just 1 second.
sir, thank you so much, sir.
Welcome.
It's
Yeah, you can
really
accept
our honor, like we got an opportunity to hear from you.
So thank you. Actually, I really enjoy, these kind of things. I enjoy. If you want more seminars later on, department-wise, also it's not a problem because we have enough time in the world now.
Yes,
No
sir.
problem.
Thank you, sir. Thank you so much, sir, for sharing your knowledge and sharing a lot of things, information, valuable information with us. Thank you so much, sir. Dear participants, we'll meet again at 12 p.m. So kindly don't miss to fill the attendance form. Fill the attendance form and submit your feedback in the hotel portal, because this attendance and mark we will upload, but feedback you people need to upload from your portal. Once you will fill, then only you can get your certificate. Anyhow, we will meet at 12 p.m. Any other queries, you can message in the WhatsApp. Thank you. Now I'm going to end the session. Again, we'll meet at 12 p.m.